Hello, everyone. Good afternoon. I hope you can hear me. So my name is Nuno Antunes from the University of Coimbra. It is my pleasure to welcome you again to the AIDA webinar series. This is a joint webinar series between the AIDA project and the CMU Portugal Program. Until September 2022, the AIDA project and the CMU Portugal Program will continue hosting this series of webinars, with 2 more upcoming on improving 5G risk management, where we hope to put together leading experts from academia and industry that are together with the researchers involved in the project. So I would like to thank you all for attending this session. In this webinar, we will have Paula Silva to talk about federated learning methods, applications, and challenges. Our speaker, as I said, is Paula Silva. Paula is a research assistant at LIAD, the Laboratory of Artificial Intelligence and Decision Support. Currently, she is a PhD student in informatics engineering and an invited lecturer at the Faculty of Engineering of the University of Porto. She has research interest and experience in federated learning, distributed-based approaches, anomaly detection, online learning, formal concept analysis, and data mining. Also, with her will be me as a moderator. My name is Nuno Antunes. It is my pleasure to moderate this session. I am a researcher with the Center for Informatics and Systems of the University of Coimbra. I work mostly with software security and dependability, also a little bit on privacy. It is my pleasure, as I said, to moderate this session and to help Paula throughout this webinar. Please interact with us. We will not have a discussion during the presentation, but you can use the chat to start posing questions that Paula will address in the end. Also, in the end, you can raise your hand to put questions directly. Paula will have her presentation, and then we will have this phase of discussion. I will be monitoring the chat, and I will make sure that all questions are answered by the speaker in the end, and that we have a fruitful discussion. So now we will move to the presentation. So I would like to ask Paula to share her screen in order to start the presentation. Paula, the floor is yours. Please go ahead.
Okay. So hi everyone, I am Paula, and the title of this webinar today is Federated Learning Methods, Applications, and Challenges. So first, this is our agenda, our outline. First, I will start talking about the main concepts regarding federated learning. After, I will talk about our work on AIDA project, which is federated anomaly detection over distributed data streams. And in the end, I will talk the conclusions. So regarding federated learning, first I will start with the definitions. The federated learning is a sub-area of artificial intelligence and is highly related to distributed learning. The federated learning is considered a new term, but it's not 100% a new area of artificial intelligence, because we can think that machine learning is a very traditional area, and we also have distributed learning, it also exists, and federated learning, which is only machine learning methods over privacy concerns. So it's a mix of cybersecurity, distributed learning, and now we have this new term named federated learning. So distributed learning has started to deal with the new world of small, heterogeneous, and distributed device, because nowadays we do not have only computers doing models. We also use devices like smartphones, wearables. So we need all of these devices produce data, and we have to integrate them and learn models using those data. So two challenges arose in data science. With the creation with the GDPR, it's the General Data Protection Regulation, now the data must be protected and the people now has total control over the data. And with the era of the big data, we have a large volume of data, and it becomes increasingly difficult to store all this data in a single location. So from these challenges, there seeks to solve the problem of building models when the data can never leave its origin. So when we have the data protected, so we have, for example, a data in a server side, and this data can never leave the server. Or for example, when we have a network of hospitals, each hospital has your own data, and we can't share this data from each hospital from each other. So now we have to build models using all this data, but without transferring the data and doing centralized approach. And so the main characteristics of federated learning is it must be collaboratively. Each node in our network have to collaborate each other and with the server to build models. It should be distributed, all the data is distributed, and over privacy preserving concerns. The critical challenges is the privacy preserving aggregation is far from trivial. It's not trivial. Aggregate aggregate models, guaranteeing the privacy preserving, and the support for several types of machine learning algorithms. Federated learning is a growing area. Nowadays, we can see several works in this area, but it focuses more on deep learning models, and it's also important to support other types of algorithms, mainly explainable models. So, for example, how looks this federated learning architecture? We work in a client-server architecture, for example, and in this case, we are doing a simple distributed linear regression. So, is the node in the middle. I named him like client node, and we have another participant node. This is the nodes who will participate in the model building. Here, these formulas are not very important, but the most important thing is to observe that between the nodes, the participant nodes, and this central node, we can only share partial calculations, and from the central node to participant node, we can only share aggregated data. And we can never share the raw data between central node and participant nodes. In federated learning, we have two main architectures. This is the horizontal federated learning and vertical federated learning. The main difference between these two architectures is the way that the data is partitioned. So in horizontal federated learning, the data set is horizontally partitioned. In this case, each node, for example, here we have data set A and dataset B in node A and B, and a central server named FL, for example. So in this case, each node holds the same features, the same set of features, but the individuals are different. And we can apply methods of aggregation on the server side. In vertical federated learning, the dataset, as the name says, is vertically partitioned. In this case, we have a partial overlap on sample ID, but the feature space is different. We have another architecture named Federated Transfer Learning. So what is transfer learning? Transfer learning is a machine learning method where we use a pre-trained model as a starting point for another model in another task. So in this case, in the federated transfer learning, we have, for example, the dataset A and dataset B. In this case, the data shares neither sample space nor feature space. At least two datasets have a small intersection, sharing only a small portion of feature space from both parties. And for the federated transfer learning, in a practical terms, it is applying using the same architecture of vertical federated learning. Another very important point is the privacy. We also have two principal types of privacy, the global privacy and the local privacy. The main difference between them is where the privacy algorithms are applied. So in global privacy, the model updates on the server are private. The secret aggregation is applied at the server side. In this case, we do not have privacy algorithms running in the client nodes, but in the server side, we have to guarantee that the security aggregation is private and to guarantee the communication between the nodes and the server. So in this case, we can apply different types of algorithms in the server side. In the local privacy, it requires private individual model updates. So the privacy concerns is applied on the client nodes between the communication, in the communication between the client and the server. So in this case, there is no one privacy algorithm applying the server, and the control is done on the client nodes. We also have hybrid approach, where we have privacy preserving methods in the server side and in the client side. Consider that federated learning is a new area, but nowadays we have a considerable amount of frameworks to deal with federated learning. It helps us with some set of algorithms, of course, but mainly in the part of the privacy and the communication between server and clients. One of those important frameworks is named FATE. The FATE is provided by the WeBank team. This is a framework developed to deal with anomaly detection, but mainly with to control credit card flows. So we have some algorithms implemented there, and the main language is Python. The most famous framework is the TensorFlow Federated. It is from the TensorFlow team. The language is the Python, and we can see a huge amount of algorithms already implemented, but the TensorFlow is more focused on deep learning algorithms and neural network algorithms. The Sharp AI is another interesting framework. It is also developed in Python. We have the Flower, also developed in Python. Since there is a few algorithms already developed inside Flower, but in the AIDA project, you choose Flower because it has the most simple architecture, and it's easy to deploy and to implement new algorithms. We do not have a lot of modules to understand and to change to make our algorithms work. It works in a very simple architecture using the server client architecture. So it's easy to implement the server side and the client side algorithms. Another interesting framework is the Data Shield. Data Shield is developed in R. It is focused mainly on not only on machine learning, but it's most focused on statistical computation. And this Data Shield is done focusing on epidemiological analysis. So in federated learning and machine learning, the model evaluation is a very important task. So it consists of assessing the aggregated model after assigning it to each client using the local evaluation datasets. Each client shares performance with the server, which combines local performance with global evaluation. So in this case, we combine local evaluation methods in the client nodes with a global evaluation in the central server. Nowadays, most part of the authors are importing these evaluation techniques from traditional machine learning pipelines. The most used evaluation metric is the accuracy, precision, recall, F1 score, ROC curves. So it's the traditional techniques used in machine learning. This model evaluation is still in an early stage, and there are several open challenges and opportunities to research. So first one is the communication efficient transitions in FEL context. In these transitions of aggregated models and partial values between client and server, it must be efficient. And another thing is it must be synchronized. Each round of computation also must be synchronized, and it's also important to have a metric to control this efficiency, the synchronization, and those things relate to the communication. Another thing is how to guarantee that the results are similar to centralized approach. So the mainly doubt among distributed approach is if the results will be similar with the centralized approach. So we have to find ways to compare them and guarantee that the distributed is working. And another challenge in this area is also how to deal with unbalanced data or poisoning attacks. So it's important to develop specific metrics to deal with federated learning algorithms. So now it's about the federated anomaly detection over distributed data streams. It's about of what we are doing in the AIDA project. Our main goal is detect anomalous behaviors in federated environments over distributed data streams. And all of this must be done using explainable algorithms. So let's expect the contribution. The first one is a framework with a set of federated algorithms for interpretable anomaly detection over distributed data streams. A federated architectural outline containing the framework and additional components, so everything that you need to deploy our experiments, and at least the evaluation methodology specifically for data strings algorithms in federated environments. So our proposed approach is split in three main activities. The first one is the federated, the framework development. The second is the anomaly detection algorithms. And the last is evaluation methods. It's important to know that all these activities occur in kind of at the same times, because at each algorithm that we have to implement, we have to do some modifications on the framework, and also the evaluated methods specific for each algorithm. So this is the architecture of our proposed approach. So in this case, we are working in a horizontal federated learning architecture. We have a central node and the add nodes, and this central node is connected with a Kafka connector. The Kafka is important to deal with streaming data and to put this data on the edge and distribute the data between the nodes, among the nodes, sorry. So we are working on three use cases. So the first use case is related to distributed attacks. The goal of this use case is detect attacks in a distributed platform involved by privacy preserved concerns. Now we are working with the distributed denial of service. And we are using the dataset VDOS 2019. Now we are working with this dataset that is available on the literature, and we choose the distributed denial of service because of this natural way of to be distributed attacks. The second use case is the phone call fraud detection. It's a use case that we are developing in partner with the CMU. So it's important to note that according to the Communication Fraud Control Association, around $29 billion is lost annually in the telecom sectors due to frauds. So it's very important to work with fraud detection in telecom. The main goal is detect as soon as possible with items with anomalous behavior. So it can be distributed behaviors, small number of calls, bursts of calls, and different types of frauds in phone calls. At this moment, we are using a data set named phone call data. It's provided by Mobilio. The use case, number 3, is the IPTV illegal access. It's the use case that we are working now. For us, it's the most challenging use case because the goal is detect illegal IPTV streaming traffic data in a distributed platform involved by privacy preserving concerns. The main problem in this is how to detect that the video, the IPTV streaming, for example, the sport TV channels, how to detect that we have a person accessing this illegally, mainly from a VPN, and how we can differentiate this illegal of the legal access. It's nowadays we have lots of services, illegal services, and they work so well that sometimes it's very hard to differentiate them. For this use case, we are using the dataset named IPTV service data provided by Mobilio. In this case, we have data flow, network flows data. So here we have an example that what we are working now. We are working a traffic analysis based video string sequence alignment. So not only sequence alignment, but we are working mainly on traffic analysis based on video streams. In this case, we have a small example using sequence alignment. So the basic idea is have different data sets. For example, data set from VPN1 and VPN2. It's important to note that the data are collected using VPNs and simulating an illegal access. So we have from VPN1 and two different VPNs or different providers. We can have two or more data sets. From these data sets, we build histograms to represent this data with different time windows. For example, with 10 seconds, 30 seconds, 1 minute, we try to find the ideal time window to work with histograms. We build these histograms using the package size, and we build an histogram using 10 bins and downstream and upstream regions. After this activity of building the histograms, we work with different techniques, for example, dynamic time warping and Euclidean distance, decision tree, and other techniques trying to differentiate the illegal access from the legal access and try to classify traffic analysis. So our conclusions. So in this project, we identified several challenges that arise from detecting anomalous behaviors over distributed data streams in a federated environment. So from these challenges, the algorithms that process data streams usually run into environments without privacy concerns. In this case, there is the need to detect anomalous behaviors through network flows with privacy preserving, and the need to build an approach able to learn models from network data streaming into a federated environment. And finally, the federated learning is a new and a hot topic in artificial intelligence. In the last months, we can see several of papers published in this area, but it still has several open challenges and research opportunities. One of them is working on anomaly detection, fraud detection, and those topics. And in our case, we are working on these topics in the area of telecommunications. So thank you.
Thank you, Paula. We now open the floor to discussion. We don't have many questions in the chat for now. I don't know if someone wants to raise their hands to start posing questions. While no one joins the discussion, I will make at least one question to clarify something so Paula, kind of a general question before going into details. You showed your approach, then you presented three use cases that are very diverse, very different from each other. How much can you use from reuse from this approach in the three use cases, or and how much do you need to implement specific for each use case?
In this case, for example, we can use the same architecture to implement all the use case. The difference between them will be the algorithms that we will use and the data, but the architecture, the federated architecture is the same. Now they are different each other because we have different machine learning tests in each type of use case. Right? In the first use case, we can use a classification test, In the use case of the phone calls, it's different because it's an approach using graphs. So it's still under development because now we are dealing with this task as a centralized approach because it's important first, made the idea works as a centralized approach and after transform them to a distributed approach. And in the IPTV use case, we are now also dealing with a centralized approach. I think this is the most challenging because this is very hard to deal with this illegal access. It is very, very similar to the legal access. So it's different to classify them in two classes, for example.
Okay, thank you. So in the use case 3, you have a particular challenge that I see here, that is many times someone that is concerned with this is behind a VPN. But is this also a challenge for the use case 1 and the use case 2, or not so much? These two use cases don't assume this challenge that the user will be behind VPNs when doing this kind of activities.
Now we are only assuming that it's behind the VPN only in the use case 3. But in the use case 1, when we are dealing with distributed attacks, sometimes they can be hidden by a VPN, but now we do not have enough data to deal with this case.
Another question that I don't know how much you can answer about this. Your solutions, assuming that that they will work and be effective in the future, right? This is research, so it's always there is no sure thing that they will work. But how will they be deployed in the system? This will work in the operators, in the network operators, right? In the SPs, right? The internet service providers, right?
Yeah. Yeah. So in the future, I don't know if it will be possible right now, but in the future, the idea is to work as a microservices. Yeah. But it is still a long way to develop it. In this case, to work as a microservice, we need to have a very fast architecture and very fast algorithms to deal with them. But the idea is to work with the providers.
So we have a question from Inês Valentin. So Inês asks, during your presentation, you mentioned several federated learning frameworks. In your solution, are you using more than one, or what are you using, or are you implementing those algorithms from scratch? I don't know if you want to go back to that slide and to clarify a little bit on that, to answer to this question. So basically, Inês is asking what are which frameworks are you using, if you are implementing the algorithms from scratch, etc.
In this case, we use the Flower framework as a starting point. We are doing some tests using the implemented algorithms, but we are also implement our algorithms inside the Flower framework. So
Flower has already implements these the algorithms that you are planning to use, already has them in a federated learning fashion, right? Already provides support for that.
Yes, in this case, we have a few algorithms, but the most important thing that we look into these frameworks is how easy and how simple is possible to implement new algorithms inside the existing frameworks. So some of them have a very, very complex architecture. In the case of the TensorFlow, it's very focused in tensor approach. So in this case, we look at not look only in the available algorithm, but the framework architecture for us in this case was the most important characteristic.
Okay, thank you. So we have two questions in the chat. I will not follow the order because the last one is more related to what we are discussing now. So Dylan Perdigão is asking, on the algorithms covered by the frameworks, we see that federated learning can be applied with neural networks, regressions, clustering. Is there a way to apply also federated learning with decision trees like gradient boosting, for example?
Yes, it's possible. From this that I showed in the step, we have others, but here I choose some more important. But mainly if this algorithm is not implemented into the framework, it's not very difficult to include this existing and traditional machine learning algorithm inside this network. The most important thing that you have to think about how distribute the algorithm in the clients, so we can build, for example, partial models in the clients, and the server side we can aggregate these models. So the important is this interaction between, for example, we can have a decision tree in each client mode, and in the server side we need to aggregation strategy to combine these models.
Okay, thank you. So Paula, going back to the use case 3, we have a question here that I think is good to detail here. If you can describe the data that you are using in use case 3, if you are using the actual content of the traffic that is encrypted data, right? Because the scenario assumes that the user is behind the VPN. If you are using just the headers, if you can elaborate on that.
Okay, in this case, the data set, we have only the headers of the traffic flow communication. So we also do not have lots of data to deal with this. So use only the headers like the destination source, origin source, the package size, and this kind of data.
Okay, and I also would like to follow up on that. Do you have already some evidence that those features, that information will be enough to detect? Do you have already some evidence that it will work, or is it too soon to know?
Now we are testing different techniques to trying to prove that this type of data using only the headers is enough to solve this problem. But for a while, we do not have very good results. So it's still a work in progress, and it's still an open question if only the headers is enough to deal with this use case.
What kind of information do you have in the headers? Information like the size of the packets and the
yes
source and destination, and what else? Anything that is relevant besides that?
Now we are working with the package size, but we also work with the difference of the time between the package, and we also have the yes, it's a header of a network flow. But the most important thing for us is the packet size, the time, and the source and destination.
Okay, one last question on this. So I think it's in the next slide. You explained that you group these packets in histograms, or not sure if in the next slide or in the other one, but what is this? What are you trying to do here with the features? What are you trying to do with these?
The question is about why we use histograms. Yeah.
Yes, this strategy
Yes, we chose these strategies based on literature. There is some work similar with this task, that is the traffic analysis based on video stream. So in the literature, the authors represent this data as a feature engineering process, as a histograms. And the authors use this methodology to build the histograms using different time windows, package size, the number of bins, and the distribution between downstream and upstream regions. So this approach is from the state of the art of the literature.
So Ines is also asking if some of the algorithms that you are using are more prone to attacks than others. For instance, if it is easier to extract private information when using one algorithm than the other one. So both in terms of the machine learning algorithms and the aggregation strategies. So I don't know who is the attacker in the scenario that Ines is saying, but so she clarified that someone that is trying to use your models to retrieve private information from individuals, for instance, someone at home. So to simplify, are any of the algorithms that you are using more prone to attack someone try to obtain private information using one of the algorithms that you are using? If this is something that you have as a concern.
Yeah, this is something that we do not are working right now, but because first we are looking for these attacks as a classification task. So in this case, yeah, we are not working in this case, and it's an open challenge and to know who is the attacker in this scenario. But in this case, the who is the attacker is if we are dealing with poisoning attacks. Nuno, if this is your question.
No, this was a question from the chat. I don't think that
Yes.
If it was about poisoning, it seemed that is really about someone trying to use these models to learn private information about
because for someone to try to use these models to learn private information, this privacy is guaranteed by the architecture, by the central node and the client nodes. And to connect to this approach, we have to configure this connection. It needs some validations, and we have to assume that the nodes are trustable. So in this case, we are not dealing with an external attack to the architecture.
Okay, so you are assuming that all the parts from are trusted from at least from the federated learning side. Okay.
Yes. Yeah.
And for now, you are more focusing in trying to solve the first problem, that is detecting the EPTV illegal traffic, to distinguish the EPTV illegal traffic, and also not so much concerned with privacy at the moment, right?
Yes. In this case, our mainly preoccupation in our work in this project is to provide federated algorithms to build models, but the privacy algorithms and the privacy approach for a while is not our main concern in this project. We are not dealing directly with privacy algorithms.
Okay, so we don't have any more questions in the chat. I think that we have a nice discussion with some clarifications. I suggest that we close here. So thanks everyone joining, for the participation, and especially for the questions. It is time to close this webinar. Please stay tuned and don't miss our next webinars. In particular, the next one will be more about security. The subject is protecting the security of the AIDA platform and the privacy of its data. And it will take place in June the 8th, 2022, with me as one of the speakers, and Claudia Brito, also coming from INESC TEC, as speakers. Thank you, everyone. In particular, Paula, thank you for your presentation and for your answers and for the discussion. And see you all next time. Thank you.